Alright, everybody, it's that time of the week again where we do programming problems together. Remember, the best way to get the most out of this channel is if you work on these problems together with me. Alright, today's problem, I was convinced by one of my friends to try out a hard problem. So far, we've been doing easy and medium problems. Today, we're going to try a hard problem. And the name of this problem is it's just called Candy, which is very appropriate since Halloween is tomorrow, and some of you might be giving out candy. Now, let's start by reading this problem together. It goes as follows. There are n children standing in a line. Each child is assigned a rating value in the integer array ratings. You are giving candies to these children subject to the following requirements. 1. Each child must have at least one candy. 2. Children with a higher rating get more candy than their neighbors. Return the minimum number of candies you need to distribute candies to the children. Okay, so imagine you had 3 children, 1, 0, and 2. You will need 2, 1, and 2 candies. Okay, you need a total of 5 candies because this middle child gets a 1 candy. They need a minimum of 1 candy. There's 1 candy on the left and 1 candy on the right. Oh, okay, so the left child has a higher rating. No, I don't get this actually. So left child has a higher rating than right child. So the left child, this child right here has a higher rating than middle child. So this guy needs to have at least 1 more candy than his neighbor. Okay, so he needs 2 candies. And third child needs 2 candies. Okay, okay, so let's look at a second example. Second example is more interesting. It says here, you can give 1 candy to this child. You have to give this child 2 candies because he or she has higher rating than this person. So they need at least 1 candy more than this person. So 2 candy, that's the minimum. And then this person actually only needs 1 candy because they are not higher rated than their neighbors. Okay? They only have 1 neighbor to the left, and they are equal. So they are actually allowed to have fewer candies than their neighbor to the left. Okay, this is an interesting problem. So my first instinct, let me see. My first instinct is as follows. Okay. Oh, whoops. This is bizarre. It's never done that before. Okay, so my first instinct is as follows. You got a bunch of children, right? Okay, whatever. You've got a bunch of children in their ratings. It's you know what? It's so bizarre. You know what, LeetCode? You are so bizarre. You are such a weirdo for rating children. These are children. Come on. We just give them the best candy nevertheless. Okay, let me see. 1, 2, 4, 1, 1. Okay. So my first instinct is to sort these children by their ratings. Okay? So that will give me this guy is 1. This guy is also 1. And then that's it. Sort the children by their rating. And then we will start with the people with the lowest rating and give them all 1s. So they have to be 1s, right? This guy has to be 1. This guy has to be 1 because 1 is the minimum. And after we've done that, we now go to all the 2s. Okay? And so for each 2, what we're going to do is we are going to check what is the minimum number of candies they can collect. They'll have to have. So this person has a 1 on their left. So they have to be at least 2. Okay? This person has nothing on their left. They're not higher than either of their neighbors. Oh, this is interesting. So this person gets 1 because they are not higher than either of their neighbors. Okay? And so this person over there needs to get a 2 because they're higher than their neighbor to the right. So let me just rating candies. So in the second round, I would go to all the 2s and this person gets a 1. Alright. In the third round, I would then go this person. This person gets a 3. The third round is 4. It's all the 4s. Fourth round is all the 10s. This person gets a 2. This person also gets a 2. Fifth round is the 13s. And then sixth round is the 23. So this... Okay, so I think this would work. This would give us the right answer. But the problem with this is that it's very slow. Because we actually end up with many rounds. We might potentially end up with many rounds. But maybe that's not a problem. That may not be a problem. Okay, so we're going to use this little trick, right? We're not just going to sort these numbers, these ratings. We're also going to build an index. That index tells us... Okay, so we're going to build an index. Basically, we're not just going to sort them. We're going to say something like, 1, 0, 1... We're going to build an index where the first number is the rating, and the second number is index of the child. So this child 0 has a rating of 1, so it's number 1. 1, 2, 3, 4, 5. Child 5 also has a rating. Second person with a rating of 1 is child number 5. So he gets a 5. And then we have the 2s, which is 2, 1, 2, 3, which is this guy over here, 2, 4, 2, 4, and then 5, 6, 7, 8, 9, and then 2, 9, 2, 9, ... Okay. So what we're gonna do is we're gonna sort it this way, and we're gonna go like this. We're gonna go to all the 1s first. All the 1s first. For each of the 1s, we will check the left and the right. Have they been filled in? Oh, actually, we don't even have to check. Okay, it turns out that this is actually pretty fast. So, okay, let me explain my thought process. So initially I thought this would be slow, right? Initially I thought this would be slow because we will be iterating through the whole array. That's what I thought. Looking for all the 1s. And then give them as few candies as possible. Oh my god. That is... this problem is such a discourse. It is such a discourse on capitalism. Okay, we're gonna go through all and give them 1 candy each. And then we're gonna go through the whole array and find the next lowest people and give them 2 candies each. But I was wrong. Okay? I was wrong. We don't actually have to do that. If we do this sorting, so we only have to go through the array once. because we're not, when we do the ones, we're not going through every element in the array. We're jumping to all the ones. So I think this might actually be fast. Okay, you know what? This hard problem is not that hard after all. Alright, so ratings. We're gonna build an index. And I feel like we've done something like this before. Okay? Let me see. Can I do this? Let's just run it. Oh, it looks like I can. None value. Okay, yeah, this works. Okay, so, and I'm gonna sort index. Okay, so I'm going to return index. Let's see what happens. Okay, so index is this thing right here. This would be index. Python sort list. I keep forgetting. So list.sort. Okay, sorry, my bad. So it's index.sort. Run it. See what happens. This should work. It should give me an error or the wrong answer. Aha! So this is what we want. 0, 1, 1, 0, 2, 2. 0, 1. So it's 0. Index 1, 1, 0, 2, 2. Okay, cool. So we have this. Now, we're gonna go through the index. We're gonna be really Pythonic about it. Okay, we're gonna do this notation, idx value in index. So next thing I'm thinking about, do we have to actively know when we're going from, we're working on the ones, and we work on the twos, do we have to actively decide that we are actually working on the twos? We don't have to, right? We don't actually have to. Okay. Answer equals, I need an empty array of size. So let's do 0 times length of ratings. Okay, so this is again a very Pythonic idiom. So what it does is it takes the array 0 and multiply that by the length of ratings. And so when you multiply an array, a list with an integer, it just multiplies the multiply this, just to make sure that this is right. It just multiplies this array a bunch of times. This would be 0, 0, 0. Yeah, exactly. This is what I want. Okay. So for each index val in array, so let's check the left and right. If I don't even have to check the left and right. Min equals, okay, we have to take the max. We find the maximum value of answer let's just say candies. Maximum of candies and candies. So we take the maximum of the left and right. Okay? If they are both 0, oh no, we can't do this. Okay. So max equals to 0. If idx greater than 0, so we're not talking about the leftmost person, and ratings IDX greater than ratings IDX minus 1. Okay? So this is a very common idiom. Again, in Python, the nice thing about this is that the evaluation for an if condition goes from left to right, or for any condition it goes from left to right. So first, it will check if index larger than 0. If it's not larger than 0, if it equals to 0, then it will return false right away. It won't even evaluate this. So this never gets evaluated. And you don't want this to get evaluated when IDX equals to 0, because this 0 minus 1 is negative 1, ratings minus 1, then everything goes haywire. And max equals to max of, well, you don't need this, x minus 1. If IDX is smaller than len of ratings minus 1 and ratings dx larger than ratings IDX plus 1. So notice there's the same thing here. First comes the condition, the check for boundary condition. So this should not be ratings, this should be candies. I should call it myself MX. This is, well, I need a different. I can do this, but this sounds like something I don't like to do. Let's just call it MX. Or I call it, well, let's just call it Maxi. I don't, yeah. Okay. Alright. Ratings. So, well, sorry, not ratings. Candies. IDX. Oh, interesting. So it's not index and value. Is it IDX and value? I want value first. So this should be value first and then IDX. Okay. X equals to maxi plus 1. Okay, so let's look at what happens here. So there are a few cases. First, ignore the boundary conditions first. All right. First, the first case is if both your left and your right are larger than you. Okay? Because they are larger than you, they would, by definition, not have been processed yet, since this index is sorted. If they are larger than you and have not been processed yet, they will get the value 0. So, maxi would be maxi equals 0, maxi equals max of maxi and this candies, which will give you 1. So you will be 1. So an example is this guy right here. Alright? When he's being processed or she's being processed, she's processed second. When, well, she is being processed, neither this person nor this person has been processed yet. So by definition, both of these would have candies. In the candies array, both of these would be 0. So you can the maxi will be 1. Alright. Take this person, on the other hand. This person is processed here. So when this person is being processed, their left has already been processed and has a value of 1. Their right has not been processed yet. So the way this works is that because of this sort over here, any number, any child whose rating is higher than yours has not been processed, will be processed later than you. So this would have rating 0, candy 0, and this would have candies 1, and you must be candies 2. Okay, in the third case, take this guy. This guy is processed like here, 2, 9, and I think the next one should be 4, 3. So the next one is this. So this person is processed only later on. Okay, cool. I think this should work. So this person in process. So the same idea extends itself, right? So for instance, this would be 1. This person, by the time it's processed, will have to take number 2. Likewise, this would be 1. This would be 2. This has to be 3. So finally, the total number of candy that this outputs. Actually, I can just say total 0, and then total plus equals return total. Okay, I think this should work. This should work for the simple cases anyway. I think the only problem with this is that it's not the absolute fastest. What is the runtime? Oh, okay, alright. I was gonna say, what is the runtime complexity of this algorithm? Well, the runtime complexity is actually this thing right here. This thing right here, sorting. This is n-o-n. This will be n log n. And then this is n. So this is actually fairly simple. Okay, so it turns out the hard problem is not that hard after all. I was lied to by my friend. Yeah. God damn it, Abby, I blame you. You have wasted all our collective times. Let me see, do I have time for one more problem? Maybe. Let's do an easy problem, but let me see if there's more to talk about on this particular problem. So is there an even faster way of doing it? I believe there is, actually. I believe there's an ON way of doing it. Not O-n log n, but O-n. So we'll go through, and the idea, so my idea is as follows. My idea is as follows, okay? I think there's an ON way of doing it. Alright, think about climbing the mountain. I want to think about climbing the mountain. I don't have to do, okay, so this sort makes it a little bit slow because it makes everything ON square, which is not terrible, right? The difference between ON and ON square is actually not that large. The difference between ON and ON log n is not that large because the log of number does not grow that quickly. So I think there's an ON way of doing it, and the way I'm thinking about it goes like this. I'm climbing the mountain, so I'm going to go 1, 2, 3, and as long as my mountain goes up, I'm going to go from left to right. If I see a higher number, then my mountain goes up. Okay? 1, and then it doesn't go, it just goes back to 1. It's still 1, okay? So my mountain goes up unless, aha, okay. So here's what I think is supposed to happen, okay? My mountain goes up when I see a larger number, so like this 1, 2, 4, it keeps going up, right? 4 will be at least 3. Now my next number goes down. So what is a solution here? Well, it's 1. Okay, that's good enough. I'm going to remember two things. One is the last peak. Last peak. Okay, and then now 2. What am I going to do for 2 is I'm going to increase to, well, I don't have to do anything actually, so it's still 1. And then now what do I do for 1? For 1 here, I'm going to do a 1, but I'm not just going to do a 1. I'm going to push everybody up. I have to push this person up. So this person has to become a 2. Oh, interesting. Okay. So what am I going to do? What I'm going to do is store my last peak. Okay? So my last peak is defined as follows. My last peak is a number that is not lower than the number before it. So for instance, when I get here, my last peak will be here. Okay? And then my last peak, because this is 1, my last peak is here. So now my last peak is here. I have to 1. I have to increase my last peak by 1. Because the idea here is that when I go down, I find that my let's say this is like let's say the next one is -1. Okay, my last peak is still here. I have to give this guy 1, and by a cascading effect, there is a cascading effect where everybody has to go up. Okay. Oh, interestingly, this person also has to peak. Oh, so the last peak is not here. The last peak is actually here. So let me see how this is gonna go. 1, 1. Okay, so my last peak is, I don't know where my last peak is. Okay, so let's say I'm here, right? I change this to 1. This has to become a 2, right? Does this have to go up? This does not have to go up. Okay, so my last peak is here. So now what happens when I see a -1? Well, this guy will be 1. This pushes the person before me to a 2, which pushes the person before me to a 3. So this still works. This still works. This 2 right here doesn't have to change because of the weird rules that they have. So basically, I have to keep track of this thing called last peak. The last peak is basically the last number that will be changed by my ripple on cascading effect. When I get a new number, if basically the rule is as follows. When I see a new number, 1, if it is higher or equal higher, it will be, if it is higher than the one before it. Let me see, if it's higher than the one before it, then its value will be Candy's I at value I will be Ci minus 1 plus 1. Yep, will be one more than the previous. If it is equal, then its value will be 1. If it is lower, then its value will be 1, and then we have to add 1 to every one until last peak. Okay, so this is interesting. This is an interesting solution because 1, it is on time. I never go back. Okay, well, it's funny. You look at this line. It says here, I will add 1 to everybody until last peak. That makes you think, okay, that means I have to backtrack on my array. I have to go backwards in my array and change the numbers. Well, the answer is actually we don't. Okay, because all we need is total. We need the total number of candies we give out. So we don't actually need a list that shows who gets how many candies. So all we have to do, total plus equals 1 plus I minus peak. Plus equals current value. Okay, so this is interesting. Yeah, well, I add 1 to it and everybody is got like pushed up. Okay, so I'm gonna try a different solution to this. I'm gonna save this as candy 2 because I'm gonna do it. This is not the right way to do things. Please, boys and girls, do not do this in your life. Alright? You see somebody doing this, what I'm about to do, they need help. Talk to them. Break that ice. Alright, cool. So here's the new plan. Okay? We're gonna pretend we're mountain climbers. Whereas as we climb the mountain, if our next number is higher, all we have to do is to add the current number. If the next number is equal, we'll push it all the way down to 1. Alright? If the next number is lower, then we are the new last peak. We are the next new last peak. And we become the new last peak. So the idea of the peak is to keep track of, like in this example, like just to push this point down, 9, 8, 7, 6, 4, 5, 4, 3, 2, 1. Okay, in this example, let's say R equals ratings equals, so candy will look like this. First, you see 9, you give it a value 1. Okay. And I think default last peak it will be, this is always the last peak. Oh, actually it's not. Okay, so 1. Okay, so you go to the next person. The next person is lower than previous value. So you would say you add 1 to this and you change this to 2. The next person, and then now your new peak stays. Your peak stays. Okay, this is not. We do not become the last peak here. The last peak is here. This is the new last peak. I don't know about this second one. But let's think about it. Okay, so my last peak is here. So now 7 is lower than 8. Alright, so 7 gets 1, 8 has to go up and 9 has to also go up. So my new value is 7 will be 1 plus I minus last peak, which is the index of this, minus index of last peak, which is 2. So that gives you 3. Alright, same thing for here. So 1, this goes up 2, this 3, this goes up to 4. Notice this cascading effect. When I have a new low, strike a sort of new low, so to speak. It's not actually a new low, but if the next number is lower than my current one, then I get this cascading effect where you push the last few numbers up. And the last peak keeps track of what is the last, where does this cascading effect end? So for instance, if this is 1, 9, this will be last peak. When I add 1, 2, 3, 4, 5, this person doesn't get affected because it's not one of the last peak. Okay? So the last peak only happens when you have a new high. Let me see what happens if this is 9. This is 9, this is 1. Okay? When I cascade, I don't affect him. I don't affect this person. So it seems like the last peak only happens in this case when the index is actually higher. When the index is higher than the one from before. Oh no, it happens in both. I see, the last peak moves. The last peak moves in both of these cases. Move last peak to this, to I. Ah, okay. And then if my next one is, let's say, 5. This will be... Okay, let's say my next one is 4. This will be 1. And what happens if I will now move the new last peak here, such that if this continues going down, the ripple effect, see this ripple effect that I'm doing? When I see a downward turn, I have a ripple effect. It's 3, this has to become 2. When this is 1, this has to become 2, and this has to become 3. The ripple effect stops at last peak. Okay, gotcha. Alrighty. I think we got it. Alright. So let's go back to description. I'm going to check a little bit of something. Okay, n is at least 1. Okay, cool. So there's at least one thing in the rating. So we're going to assume that the n is at least 1. So for R, which in rating, current equals to rating 0, peak equals to minus 1. So there's no last peak yet. And now we start from the first one. Okay, if R in ratings 1 colon if, well, not current, actually it's previous, if ratings, if R is larger than previous, L if R equal previous, L or else it has to be smaller than previous. Do this. Okay, if it's larger than previous, then its peak value I think this should be 0. Okay, we can check out logic later. So if it's higher, then total equals to 0, right? Total equals 1, because the first person, the first guy gets 1 candy to start with. Okay, so if R is larger than prev, then total plus equals previous is 1. Previous candy total equals to 1. Okay, then plus equals previous candy equal ratings. R is you know what? I'm gonna do my we do this instead. Enumerate. If IDX, if value rating is larger than prev ratings IDX minus 1, I'm gonna make this better later. Okay, so 0, then previous candy. Okay, I'm gonna fix it later. Okay, so if rating is larger than previous candy, then total plus equals to previous candy. Yeah, previous plus 1 plus equals 1. So my new person, sort of current candy, is equals, let's do this in the most prev candy plus 1. So let's show what we're actually doing. Show our work. You know what? Show our work. Equals total plus minus current candy. Previous candy equals current candy. Okay, this is if we're going up. And peak equals to IDX. So this is the new peak. If R equals to ratings, if rating is same as ratings is the previous one, then current candy equals to 1. Right? We reset all the way down. Just like in this example over here, we reset all the way down. Total plus equals current candy, yep. Previous candy equals to current candy, yep. And peak equals IDX. Okay, so third one, which is interesting case, when rating L, if rating smaller than ratings IDX minus 1. Okay, so current candy equals 1. Total plus equals current candy, which is plus 1, plus the cost of shifting the peak. So IDX minus peak. Previous candy equals to current candy, and peak is unchanged. I think this works. Just for the sake of completeness, if IDX equals to 0, peak equals to IDX. Total. Yeah, I don't. Let's just leave it. This should work. Okay, so basically what it's doing is essentially codifying this. And the nice thing about this algorithm, if it works, I don't know if it does. Let's run it. Yeah, I always fall for this. Oh, and I have to return. There was another error. Solution to candy. Is there candy? It's my candy. Did I use candy? I did not use. Come on, guys. Where did I use candy? Oh, candy. Ah, gotcha. Here, let's run it. I think this should work. If there's an off by one error, okay, let's submit it and see how fast it goes. It should be faster. Wrong answer. So 131. "24 out of 48 test cases passed. 0 ratings. So you go down a peak. What's happening? Let's go back to our trusty visual debugger. Okay. Let's take candy, rating self, blah blah blah. Let's put it here. Just ratings and no self, because we're selfless like that. Okay, what's the one that... We're gonna print candy. It just takes a rating, right? Rating. And visualize execution. Let's see what we get. Okay, so we ran it. Okay, let's just put breakpoints here, 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 and here, and then and here. So let's go to this one. Okay, so when IDX is 0, okay, total is 1. It's going to continue, yeah. Okay, now IDX... What is IDX 1? Oh, IDX is 1, rating is 3. Okay, cool. Peak is 0. Alright, cool beans. Current candy equals to previous candy plus 1. Previous candy is 1. So this guy has 1 candy. This person should have 2 candies. So next. Previous candy, current candy is 2. Previous can. What's happening? Okay, total should be 3. So 1 and 2. Right? Oh, I can do this manually. So now... Okay. So now index is 2. What is rating? Oh, index is 2. Rating is my current rating. It's 2. Okay. This is smaller than the previous one. Peak is 101. Okay. So moment of truth. So it should be IDX minus peak. So this is 1 candy, 2 candy. Oh, because I'm not causing a cascading effect if the previous person is already 1 larger than me. Ah, drat. So I think my strategy doesn't work at all. My strategy doesn't work at all because so strategy doesn't work at all. Okay, you know why? The reason is because now I keep track of the last peak to know what my cascading effect is. But my cascading effect don't always go to a last peak. Wait a second, is there a way I can do this? So this is 2, right? So this will be 1. So my last peak should move here. Oh, I need multiple last peaks. So the thing about having one last peak and keeping track of the cascading effect is that I'm assuming I made the assumption when using the idea of the last peak, right? If I only keep last peak, then I'm making this assumption. You see how when one of these move, all of these guys before have to move up. It has to move up. That's my idea. That's my assumption. That's why that's an assumption of last peak. But if let's say r equals, I don't know, but let's say c equals 1, 2, 3, 4, 5. Okay, so it went up very high and then it went down back to 1. Uh, 10, no, 11, 12, 13, 14, 15, and then it went back to 11. Let's say it went back to 11. Okay, you know what? Let's say it goes back to 1. Okay? So let's say this is my R. Let's say this is my R. Okay? So it keeps going up, and this is 1. Okay? It goes down, but it doesn't push this person up because there is a huge gap. It only pushes this person up if this is like 6, 5, 4, 3, 2, 1. So this is 1. This pushes it up. 1. This pushes up to here. Then my last peak is actually here. 1, 2, 3, 4. And then when this comes here, this pushes the one before it. 2, 3, 4, 5. Oh, in my previous case, my last peak is here. So this becomes 6. So this is my new last peak. So this becomes very insidious. This is a problem. Okay? Which means I have to keep track not just of the last peak. I have to keep track of troughs. Not just of the last peak, right? Not just the last highest number. I have to keep track of drops. I need to keep track of sharp drops. You see this sharp drop here? Becomes 3, 2, 1. Can that be 2 sharp drops? This is a sharp drop. And then this is like a double peak. This is my last peak that I'll be affected by. This is my sort of double peak. Yeah, there can be multiple sharp drops. Think about it this way. 1, 3. Wait, there can be only one sharp drop, right? Can there be more than one sharp drop? I think so. There might be a way to do. You know what? There might be a way to salvage this problem. But I'm not going to do that. Instead, I'm going to submit my O1 and call it a day. Well, maybe we'll think about it next time. Maybe we will. What are you talking about? Oh, yeah. Okay, so maybe we'll call it a day. Maybe we'll pursue this new attempt. Later, okay? Maybe we'll pursue this new attempt. Actually, let's look at the solutions and look at what other people do. Optimal solution. Oh, interesting. Oh, interesting. So I think it's very similar to this. It's similar to this, but assumes that it comes on both sides. I see. In Hindi, oh wow. Ah, okay. So I think this, I see. So there's an even better way to write this. There's an even better way to write this. Okay? But either way, as usual, our goal is not to strive to find the answer to the puzzle. We're not trying to solve the puzzle. We are just learning new ways to program. We'll try and learn new ways to think about the problem. They may not be the sort of optimal solution or the correct answer to the puzzle. Because this one I think requires actually a little bit more math to do the proof that if you approach it from both sides, you actually get the right answer. The goal is not to solve the puzzle. The goal is really to explore different ways of programming. Okay, so that's it for today. I'm signing out. Thanks everybody for watching.